Good morning, good evening, good afternoon, wherever you are on this planet, and welcome to our special edition of a SETI Live. Today, we are going to talk about breaking news that's been spreading around on the internet and our favorite newspaper, as well as scientific magazine, the discovery with the James Webb Space Telescope of potential exoplanet very close to us, an exoplanet orbiting Alpha Centauri A. This is an amazing work, quite complicated. It has been published in two papers. We can put references here. And to help us going through the analysis maybe, and also some results and some thoughts on this matter, we invited Julien Girard. Hello, Julien.
Hi, Frank. Happy to be with you today.
So Julian is an astronomer and instrument scientist at the Space Telescope Science Institute, STSCI, and he's going to tell us a bit more about his work, as well as commenting on this remarkable discovery that was announced 7 hours ago. I was driving for the weekend, and I saw that, and I decided that, you know what, we're not going to let you have a weekend without hearing from us. So Julian and I put together this last-minute special edition of SETI Live. Thank you very much, Julian, for being available. I know it's been a stressful week for you, so I appreciate you took your time.
You're very welcome.
Okay, so Julian, when you heard about this news, what was the first thing that came in your mind, first of all, as a human being, as a scientist, maybe?
Though I'm not part of the team, I knew about it before. So because several members of the team work with me at the Space Telescope Science Institute and also in Caltech and other places. So we've known about the program for a long time because it's a very difficult, very challenging observation to carry out with the James Webb Space Telescope. So a lot has been done to actually make that possible in the past couple of years. And I know the team working on the data hands-on has been going back and forth between believing it, not believing it, improving the signal to noise, etc., until they finally are more confident. And so I knew they had something. I didn't know all the details, but I basically saw it coming.
Okay, so you have inside information. All right, let's talk about how this discovery has been possible. They use what they call coronagraphic techniques, using the MIRI instrument to to remove the starlight. You're an expert in this field. Can you explain to us exactly what is JWST, what is MIRI, what is a coronagraph, and what exactly they've been doing?
All right, so JWST, the James Webb Space Telescope, it's a telescope that has a honeycomb type of shape, like this cork board I have here, because I'm kind of a fan. It's been launched on Christmas Day 2021, and it's been commissioned during the first months of 2022. So it's been 3 years that we are in operations now. It's a 6.5 meter across primary mirror, which is golden coated. So it's I'm sure most viewers have seen images of the telescope before launch or some rendering. It's in space at about 1 million miles from Earth in the Lagrange point. It's some kind of stable orbit where it's really cold and really stable. So the environment is perfect to do infrared observations. On Earth, we can do some infrared observations, but we are limited by the atmosphere, but also by the optics and the sky. Everything radiates in the infrared, just like us. Basically, that's how we can see ourselves at night with infrared goggles. So basically, that's why we put this kind of telescope at this location in space, to have such a stable environment that we are much more sensitive to those wavelengths. And then coronagraphy. So JWST has 4 cameras, four instruments, science instruments. It has a few more for guiding and so forth. And the MIRI instrument is the one that is enabling the farther into the infrared observations. So basically, MIRI can observe up to 28 micron in wavelengths. And in this case, this observation has been done at 15 micron, which is something that's not possible from the ground because of the water absorption in the atmosphere. And it was using a coronagraph. So a coronagraph is some kind of mask to basically attenuate the brightness of a star and try to see something faint around it. So particular planets or circumstellar dust or something like that. In this case, the big breakthrough is that the Alpha Centauri system is the closest to Earth. So this is a star, it's a group of stars that are about 4 light years from us. So it's really the closest neighbors we have to the sun. And so it's a really big deal to actually try to find a planet around those 3 stars, Alpha, Beta, and Proxima.
Yeah, we astronomers have been trying to see that, to see bright, to see planet around Alpha Centauri A and B and Proxima for several years. I remember that in 2019 there was a paper on the potential detection as well. Could you tell us a bit about this?
Yeah, so that was my previous workspace in Chile. So the very large telescope, the European Southern Observatory. So they have a 8-meter telescope on the ground, and they adapted a mid-infrared camera called Vizier, and they made this project called NIR, which was basically combining adaptive optics and this mid-infrared instruments. And they spent close to 100 hours, so about 10 nights of observation on Alphasen A and B. And so that was I think observed in 2019. It was really a technical feat to do that, and they achieved almost space-like sensitivity at 10 micron. They couldn't do 15, but they did 10 micron, and they were not sure to have found something, but they found some kind of blob that they called Candidate 1 C1 in the Wagner et al. 2021 paper. And they mentioned that it could be a planet of bigger than Earth, smaller than Jupiter, but they were not sure about it. So it was reported as potentially interesting, but it remained a candidate for many years.
All right. Let me say hi to people watching us from Florida, from Switzerland, from Australia, from Northern Virginia, from Colombia, and welcome. We are talking to Julien Girard of the discovery of Saturn, potentially Saturn-like exoplanet around Alpha Centauri A, a closer star to our solar system. All right, I'm going to ask very naive questions here. There is 2 papers for this discovery, right? And I look at those papers, like you, I decided to look at them briefly, and it's multiple pages, ton of figures. It seems to be very complex. Can you explain to us why such a discovery needs to be in 2 scientific papers, and why we just publish a pretty picture of the planet and be done with it?
So I didn't read everything of those 2 papers yet, because as you know, they just came out. But what I know is that they are very long, because the technical justification to basically explain the readers that this is rock solid and it cannot be an artifact is very long. Also, the background on how to explain how to do those observations is not trivial to explain. And so I think if they had done a very short paper, the community would not have believed it. They really needed to include a lot of details, including some pretty ugly data processing steps. And I'm looking at the paper right now. I mean, the two papers. And then also, I think there is a little bit of the two first authors are they are basically, one is first on one paper and second on the other. And there is a young PhD student at Caltech, Aniket Sanghi, and there is a more senior exoplanet scientist, Chaz Beischmann, and they both are the lead authors on both papers, basically. So I think the first one, so it's called Worlds Next Door, a candidate giant exoplanet image in the habitable zone of Alphasen A. The first paper is one, observation, orbital, and physical properties, and exozodi upper limits. I will explain what it is after. And the second one is a little bit more detail on and what the sensitivity, what it means to have found this planet, potentially these planets around those stars, which are a system of 3 stars, in fact.
Yeah. So I like one of the papers describe a lot about it's like a thesis, basically. There's a lot of different methods to detect, to analyze the data. You can call them CLIP, RDI, SDI, etc. These are zoo of method to do coronagraphic analysis if people are interested in knowing more. And then there is a paper. The second paper is more about the interpretation, kind of the discovery, and as well some kind of study of if it's a background object, if it's a front object, etc., etc. So I really like those two papers. I wish I had a bit more time before having this discussion, but I get the gist of it. I got now what this could be. So what do they call it? Planet candidate or detection hint? Why they don't say, hey, this is a planet? What are the reasons for which we cannot say we have discovered an exoplanet like Saturn around Alpha Centauri A?
So basically, when you do high contrast imaging, in this case coronagraphy, it's a very tough thing to do, because you basically are trying to image something that's several 100,000 times or 1 million times fainter than the star. And there are many optical artifacts that remain, and also detector artifacts, bad pixels and so forth. Infrared detectors are pretty ugly in terms of camera compared to something you have in your phone. And so when you find a blob that it's at the limit of the surrounding noise, you have to be really sure that it's not an artifact. And so to do that, we have several ways to test. One way is to observe it at 2 different angles and see if the signal has moved accordingly to the orientation of the telescope. One and other way is to observe at different epochs. So let's say observe in a certain date, and then a few months later or the year after, and see if the planet is still at the same position or at the position you expect. And sometimes that's how you discriminate between an orbiting planet and a background galaxy, for example, or a background star. But so there are many things you need to do to be sure. And in this case, because it's Alphasen system at only 4 light years from us, the whole system is actually moving with respect to the rest of the stars at a pace which is pretty high for stars. It's not exactly static. And because it's so close, also, we expect a planet to actually have its own orbital motion between months 1 and month 6, for example. Mm-hmm. And so it's possible that you observe at epoch 1, and at epoch 2, you don't see anything, but it doesn't mean it's not there. It means it's maybe behind the coronagraph, too close to the star.
Yeah, that's what happened. Apparently, they detected it in 2 dates in August 2024, and they attempted to observe it again in 2025, beginning of this year, and they did not see it.
So, in fact, they did. So in the end, they have 3 sets of observations, and in some of them, the second orient didn't work, In some of them, so in the they have one detection and two non-detections. So you could say it's not enough. If you only had that, that would not be enough. But the 2021 paper, the one from the ground-based team, the Wagner et al. 2021, they also had reported some blob on the other side, which had sort of a compatible brightness for the, let's say, same, similar size planet potentially. So what they did here is they assumed they were the same object that had basically orbited around the star during all those years, and they looked at other observations like radial velocity observations, which is something that gives you the wobble of the star and basically what kind of planet you could have without seeing them. And with combining all that, they find that there is a 52% chance that if the candidate from Wagner and the candidate from this time is the same object, then it's normal that it was not seen during the second two epochs.
That's actually a very cool result. That's, I think, one of the coolest thing of this paper. In fact, that
they did a really nice collaboration between the two teams. They invited the former team into the new team to actually get this to make that possible. So it's still not 100% sure, but it's starting to be quite compelling, I would say.
Yeah,
but we need more observations.
We need for more observation. That's the conclusion of every talk we give in science. But let's assume that this is truly a planet. So what do we know about it? I've been looking at my notes. So it's Jupiter, Saturn. It's what's the temperature? Do you have some information about the planet?
Yes, so it's bigger than Earth for sure. It's of the order of the size of Jupiter or a bit less, so maybe like a Saturn planet. Definitely a gas giant. At the separation, though, it's a bit closer to the Earth separation. So we're talking about 2 astronomical units, so 2 times the distance Sun-Earth. So it would be a little bit of a bit like a Jupiter, Saturn, but closer in with respect to what we have in our solar system. The temperature is 225 Kelvin, and that's about minus 50 degrees Fahrenheit or Celsius, because they merge at minus 40, so it's kind of the same. So it's around minus 50 degrees, so it's pretty cold. It's very cold, actually. And this is something that's really hard to do from the ground and with the Hubble, for example, but with JWST, it's much easier to see cold planets like that.
Okay. And also the planets, the star are relatively the same age than our star. I mean, the Alpha Centauri A and B have an age of 5 billion years old, roughly. So here we're talking about a system which is very close in age to our system.
Yeah, especially the A component, so the alpha component, Alpha Centauri A, sorry, is a G star, just like the sun. And so temperature-wise, it's similar to the sun. And its age, 5 billion years. It's slightly more than our sun and Earth, but it's not that much more.
Okay, we're going to take some questions from the audience. There is some. I just want to say hi to people who join us from Idaho, from Romania. We are talking about the discovery of a planet, a Jupiter-like exoplanet in orbit around Alpha Centauri A, and also people from Florida and from the Silicon Valley in California, Miami as well. I mean, we have a lot of people. This is an interesting topic, of course. The press is talking about it, so I can imagine that people want to hear from the SETI Institute and our colleagues what we think about that. So we have a binary system with 2 large stars. One is a sun-like exoplanet, and it has potentially in orbit around it a Jupiter or Saturn-sized exoplanet orbiting in eccentric orbit. maybe. Okay. What does that tell us about the system itself? Like, let's assume it's real and it's confirmed in a week, in a month or two.
Well, it's going to take longer to be sure, but yeah.
Let's say in a year or two. Yeah. What can we say about this system itself? Why is it interesting for scientists, astronomers, and maybe for SETI?
I mean, it's super interesting because we want to find life outside the Earth, right? So whether it's in the solar system or outside the solar system. And so for the whole branch of research, which is astrobiology, and finding life elsewhere, where you have the most chance of finding life outside our solar system is the closest stars, because those are the stars you can study with the most details. Also because the closer the star is, the more basically you can separate something with your given size telescope, right? So we will always observe the Alpha Centauri system, always, beyond our lives. It's always going to be studied because of that. And some people even, project to eventually send some little probes all the way there, with the solar sails or something, like light sails. And so basically, yeah, we wish to find something around those, because if we find something around the Alpha Centauri system, then it will be much easier to study than if we find, say, something 10 or 100 times further away. The other thing is that, okay, it's a binary, so it's actually 3 stars, but the third star, Proxima Centauri, is much further away. It's actually the closest to Earth, but it's much further away. It doesn't really affect let's say this binary system of Alphasen A and Alphasen B. So and then the other thing is that if we find something around, let's say A in this case, given the mass of that object, it will basically prohibit the presence of something else at a certain distance, because you have this dynamical interaction between different bodies. The same way the planets of the solar system are found basically their stable configuration after some time and are located where they are with respect to each other. The same is true in this case. And so I think, because this is 2 stars that are a few, sorry, I think it's a few, it's between 11 and 35 astronomical units, I think, between A and B. Mm-hmm. So they're pretty close. So it's not like you can have any planet orbiting those stars. Basically, at 3.8 AU or so, you can't really have a stable orbit. A planet in between would either get ejected or get attracted by one of them, I think.
Yeah.
So yeah, it's pretty interesting. Then there's even, there are a bunch of sci-fi pieces that have been written and shot in movies, assuming that there was a habitable planet or moon of a planet around Alphasen stars. So potentially in the future, that's where the human species could go, etc.
So you're talking about Pandora.
Yeah, one of the most famous example is the Avatar movie with the Pandora, which is basically a moon of a Jupiter-like planet around Alphasen star. So it would be basically a moon of this newly discovered planet.
That was a question from Sridhar Ramanathan. So we answered to it, Sridhar. Yes. Around for a very cold planet like this, a cold gaseous planet, we don't expect to find life as we know it. But maybe there is moons, and maybe these moons have an atmosphere. So it could be like a Pandora-like world where we have this life, any type of life. Okay, we shall see that in the future, of course. I have a question for you. You are working on this new project called the Roman Grace Telescope.
The Nancy Grace Roman Telescope, yes.
Yeah. But tell us a bit about it, and what do you think this could this telescope help?
So it's basically the next NASA flagship telescope. It's supposed to be launched in 15 months. So that's pretty close. That's basically at the end of next year, if everything goes well. Everything is on schedule and on budget, which is kind of unheard of in astronomy, I would say, but like an incredible feat from NASA and partners. And so it's kind of a more dedicated telescope than JWST. It's a 2.4 meter telescope. It's the size of the Hubble telescope in terms of mirrors. And it has only two cameras. The main camera is a wide field camera, so it's basically something that will raster and map out large portions of the sky. So we call it a survey telescope for that reason. In the near infrared, so it's kind of like 100 times the field of view of the Hubble, but the same kind of sharpness. And so it will basically discover a ton of things. Everyone's going to use those images. But it's so many different science cases, from dark matter to galaxy evolutions to astrometry to micro lensing. So it will find also a lot of exoplanets, but these exoplanets will be impossible to study in details because it will find it around stars that are really far away. But it will be important for demographic study and basically understand how many planets are there in the galaxy. And then it has a second camera, and the second camera is the coronagraph instrument. So that's my field basically, and that's the opposite of the other one. It has a tiny field of view, and it's really made to observe one star at a time and look for planets, just like it was done here on Alphasen, but in the visible light and in reflected light. So instead of using the thermal emission of the planet because it's a little bit hot, in this case, it will really be about observing planet in reflected light, just like we see with our naked eye Jupiter in the night sky. It's reflecting the light of the sun.
So this instrument will have the capability to detect Saturn, Jupiter, but also fainter, smaller planets, right?
No, so for the Roman coronagraph, we hope to reach a contrast of 1 billion, so 10 to the minus 9, so 1 billion, and that will bring us to something like a Jupiter in reflected light, maybe a bit less than Jupiter, so maybe something like this. Like the Alphasen planet could be possible. I don't know. The problem with Alphasen is that Alphasen B is actually very close in the field of view, and it's really basically contaminating the whole scene. In those two papers, they spend a lot of time explaining how they basically remove the light from the B star. And for Roman, it is being studied. Like some colleagues at NASA Ames are particularly motivated to attempt the Alphasen system using the Roman coronagraph, but it will require some special observing techniques that's not yet completely supported, I would say.
Yeah. So at the SETI Institute, we also have a project called Project Blue, which is basically a 40-centimeter telescope equipped with adaptive optics system that allow to also reach 10 to the minus 10 in contrast for Alpha Centauri A and B after observing the stars for something like 10,000 hours. So it's basically a dedicated telescope for one target, or two in this case because it's A and B, but two star systems, and to be able to nail down and see the surrounding of this star system.
In reflected light as well.
In reflected light. So invisible. That's why we call it Project Blue, because in our case, the goal was to really see the planet in visible light. So this is not yet flying, but it's a project that will may probably be accelerated as we discover more interesting objects or planets around Alpha Centauri system, in the Alpha Centauri system, of course. Okay, one final question for you. I know it's late for you over there. You are on the East Coast, but so we are. This is a very interesting moment, I believe. I know we always say that, but I think this is an interesting moment in the study of exoplanet science. If this is confirmed, we will have discovered something very interesting that we can study very well because it's close to us. So what do you think is going to happen in the next 5-10 years in the field of exoplanet, and specifically for the study of the Alpha Centauri system? Imagine we give you an infinite amount of money. What will you do?
No, so I'm going to start with no extra money, just what we have. It's already pretty good.
Okay.
So what's going to happen? So the James Webb Space Telescope just got started, right? I mean, it's been only 3 years. It's on sky, and it's going to last about 20 years if everything goes okay, right? And that's because the fuel, so little fuel was used to correct the orbit, etc., etc. It was launched very well. So unless the instrument break inside the instruments or something, it's probably going to last about 20 years. And so when we look at what we did already in those last 3 years, this is just a small, this is an important result, but there have been a few mature planets that have been imaged. One with MIRI, another one with MIRI, the Epsilon Indi AB. I'm gonna mix it up, the name, but the Matthews et al. Paper 2024, I guess. And that was a planet that was also very cold. And there's also the 14Her C planet that was imaged with NIRCam, which is the instrument I support the most in coronagraphy also. This is for me already a breakthrough, because those cold planets could not be imaged directly before. And so I expect in the next 10-15 years that we will detect more of those. And those are, even though they're still, Jupiter's, Neptune, maybe down to between Neptune and Saturn-mass, we won't be able to get to the Earth-like regime in direct imaging. We'll still learn about their occurrence, around the nearby stars, and that's really important. Then with the Roman coronagraph, I really hope that we imaged for the first time a few of those planets in reflected light. And that's particularly important because Roman is making use of some kind of adaptive optics technique in space. So we call it wavefront control in space. So it's basically, it has a couple deformable mirrors which are compensating for all the imperfectness of the other mirrors and the system, almost in real time, though it's pretty slow in space. And this is the first time we do that in space. And that's how we will reach this contrast of a billion. And that's super important because this is exactly the technology we want to show works in space before we launch in some, in 15, 20 years or so, the new telescope that you may have heard of, which is the Habitable Worlds Observatory, which is a flagship mission that's not yet funded, but it's been under study right now. There was a conference last 2 weeks ago in DC about it, and they already have like some preliminary designs. And the interesting thing here is that this is a flagship like the James Webb, but it will the prime science case will be our science case, will be imaging Earth-like planets directly and taking a spectra of them. So basically looking for biomarkers and life outside the solar system. So that's what really keeps us excited at night, I would say, is to basically be working in this field where post-processing techniques, coronagraphic techniques, they all come together towards that goal of one day, hopefully imaging an Earth-like planet and studying it.
Thank you very much, Julian. This is exactly what I wanted to hear. This is the first step, JWST, Roman, then the Habitable Observatory. And we see. It's gonna go. We see. Maybe in 20 years we have a picture of Earth-like exoplanet. Maybe, hopefully.
Yeah, it's still gonna be a blob-looking thing, but it's
a picture of
amazing,
the world, and with life, maybe. Okay, good. Thank you again, and I'll let you go to your weekend. We keep in touch. If you have any news, let us know. Julian and I, we know each other for more than 20 years now.
So, I think it was 2007 or 2008 when I came to the California for
your first talk after your PhD.
No, I think we observed at Leak Observatory, and then you helped me get this talk at the Center for Adaptive Optics in Santa Cruz.
20 years later, we are an institution where we are searching for life on exoplanet or building instrument, which is pretty cool. All right. Well, thank you. I appreciate. Thank you, everybody, our viewers, for watching this special SETI Live. We are, you know that you can support us by going to our website, seti.org. We change it, by the way. So send comments if you like it. And if you see some problems, just to let us know. You can make a small donation to help me to go to see Julien STSCI, for instance, at seti.org/give now. You can also support this program by liking this video, subscribing, watching us on every platform, sharing this video, and and just talk about astronomy and what we are doing, us at the SETI Institute, but also at the Space Telescope Institute, where Julian is working. Thank you again, and I see you in a few weeks to talk about another exciting discovery in the field of astrobiology. Bye-bye.
Bye. Thank you, Frank.